Shall I start or?
Yes. Can you put the yeah? Can you share your screen?
Okay.
Okay. So welcome everybody to this week's Majorana-Raychaudhuri seminar series. Our first speaker is Kazuyuki from Manipal Center in India, and he's going to talk about internal structure of the deconstructed Dirac magnetic monopole. I'll send you a reminder when maybe 5 minutes are left.
Okay. Okay, thank you for the introduction, and I'm happy to be here. Yeah, so this is the title of my talk, The Internal Structure of the Deconstructed Dirac Magnetic Monopole. So I will explain those meaning in the talk. So this talk is based on this paper, and all the details I may not come to can be found in this paper. So this is a plan. So it's just 30 minutes talk. So I'll give introduction, then the internal structure of the deconstructed Dirac magnetic monopole, which is the main of this talk, and summarize and do future directions. Okay, so firstly, what is dimensional deconstruction? So I think probably most of you are already familiar with extra dimensions and Karuta-Klein reduction. So ideally, it's beside 1+3 dimensional space-time, we see there's a small, tiny extra dimension. But if your resolution is not good, you cannot see it. So it looks like 1+3 dimension. But if you go to short distance or higher energy, then you begin to see extra dimension. So the idea of deconstruction, deconstruction is to mimic this extra dimension by lattice, but lattice in the internal space of the particle physics model. And if you are familiar with lattice gauge theory, you can understand it quite easily, but never mind. So we have a discrete point, and which is periodically identified. And if you have a many lattice points, it will cross to the continuum limit. And to explain you the motivations and historical background, let me start from gauge Higgs unification model. So this is a model to identify the Higgs field as an extra-dimensional component of gauge field. So the problem people want to solve is that light mass of the Higgs field, so-called gauge hierarchy problem. So if Higgs comes from gauge field doesn't have mass. And even after compactification, its zero mode can have light mass, but its quantum collections are suppressed, and you can get it can explain the light mass. And so Higgs theory and slow roll inflation model building, so they have a similar problem. So in the slow roll inflation model, you have to explain the flatness of the inflaton potential. So a similar idea was used and called extra-natural inflation, and it can achieve the large field inflation model. But somehow this model was hard to build in string theory. Then there's some proposal that actually this direction is strictly restricted. So that is called weak gravity conjecture. Small coupling is required to achieve large field inflation, but small coupling is forbidden by weak gravity conjecture. Now we are coming to the dimensional deconstruction. So we are discretizing the extra dimension. So I will explain the more detail, but the motivation is similar. They wanted to explain the lightness of the Higgs mass. And it is natural to look for corresponding inflation model looking at this. But actually already in this paper, it was noticed that there's a problem. The parameter regions, you can use this more somehow you can difficult to achieve the inflation, large field inflation. Well, nevertheless, we tried actually. Well, not directly resolving this problem, but we have sort of circumvent the problem, or couldn't really resolve the problem. Unnatural remains. And also, we constructed a similar model to this construction. Instead of deconstruction, we propose spontaneously created fuzzy extra dimension model. That's also a related model with similar motivation to explain light Higgs field. So by this slide, I want to kind of give you the background and motivation to study this deconstruction of dimension. So now I come to the model. So the action is given by the copies of Maxwell action. You are familiar, this part. But so copy means, so each lattice point, there's a Maxwell theory, and there's a copies from j equals to 0 to j equals to n minus 1. And so the pictorially it's like this. So this is a latticized extra dimension, and Higgs field is connecting the sites, neighboring sites. But this is still not the deconstructed dimension. We don't have the Kazakh modes discrete version yet. So in order to see, okay, that I'll come to later. But the symmetry of the model is discrete translation on the lattice, and gauge transformation. So each lattice point, lattice site has a U1 gauge symmetry, and there's n of them. So in order to go to the deconstruction of dimension, we consider the Higgs potential such that Higgs field has a finite value, and for all the sites the same value. And to be explicit, we can consider this kind of quite familiar kind of Higgs potential, quartic potential, except it has from j equals 0 to n minus 1. And yeah, this is, you can verify immediately. So around the vacuum, you can decompose the Higgs field with the radial mode and the angular mode. So this is unitary, or actually U1 number. And the radial component has mass of this order. So what is the mass spectrum? So mass eigenstates is actually given by discrete Fourier modes. So going from the lattice space to its Fourier space. And it mimics the Kazakh mass spectrum as n goes to large. And there's only U1 part is remaining unbroken. We call it unbroken U1 diagonal. It corresponds to zero mode in the extra dimensional language. And zero mode means so like a field has the same value on all the lattice sites. It's like a constant function. So now we go to the low energy below the gauge symmetry breaking scale, below the radial component Higgs mass. Then the effective theory is described by is action field, which we only like a U1 unitary matrix, one by one number, and you can write in exponential I AF. So A is a Hermitian, actually just a real number, the real field. And if you write it in this way, and if you are familiar with lattice gauge theory, this is nothing but a link variable in the lattice gauge theory, with A interpreted as a lattice spacing, meaning the space between the two neighboring lattice points. Okay. So here is a little bit remarks. Another route to arrive at deconstruction is via quiver gauge theories proposed by these people. And in this case, the link field is analogous to pion, which comes from as Nambu-Goldstone mode of chiral symmetry breaking. And this approach has an advantage to be applicable up to 4 pi f. F is like a pion decay constant. And we will follow the Higgs model of deconstruction instead, which breaks down a little bit earlier than this UV cutoff, perturbative UV cutoff. When this quadratic coupling of Higgs potential is smaller than 1. But Higgs model has advantage for our study. It provides more natural UV descriptions for the composite magnetic monopole we discussed below. So what we are interested in is Dirac monopole configuration in this.
You want good at
Yes?
You want.
Hello? I can't hear you. Hello? I think someone was muted. Yeah, muted, I guess. H. You're asking something about H. A Higgs field, yeah, Higgs field. So radial component. So its radius is fixed with some fluctuation. Then it becomes a U1 field, which becomes a link variable in terms of lattice gauge theory. Okay, maybe I continue. So, yeah, so, the monopoles and instantons are important in various places. So let's study magnetic monopoles. So in the continuous case, if you have S1 continuous extra dimension, if you just trivially put Dirac monopole at the same place, it is still a solution. And it's like a monopole string wrapping on the circle. And we consider similar configuration, but now it's discrete. And it's identified like a discretized sample. And this direction is three-dimensional space. And you put monopole from U1 j equals to 0, j equals to 1, etc. From each U1, you put one unit charge magnetic monopole in that gauge group. So this is still a solution. But there's a puzzle. Dirac magnetic monopoles, each from each U1, on top of each other in three-dimensional space. This is a solution as I just mentioned, but it is an unstable solution because each monopole, I call it like a constituent monopole. So each monopole has 1/n unit of magnetic charge under the unbroken U1. So if you combine n of them, you get unit charge magnetic monopole of unbroken U1 gauge group. But if you look microscopically, so this configuration is made of monopoles with 1/n unit charge. So they repel each other. They have the same sign. So the solution is unstable. When the monopoles are exactly on top of each other, you can't push. But if you move one little bit, then that will be repelled and unstable. But on the other hand, if you consider continuum limit, you have a stable solution, Dirac monopole string solution. So this indicates that they are somehow bound to each other. So how? So this is the main theme today. So I hope you understand the puzzle we are trying to solve. Okay. So to tackle this problem, let us start from the simplest case. So n equal 2 means there's only 2 lattice points. So there is a magnetic flux, so broken U1, and that goes from somewhere, from the source to sink. And in the Higgs phase, it is well known that magnetic fluxes are squeezed into Nielsen-Olsen magnetic flux tubes. It's like a type 1 superconductor and Meissner effect. So this magnetic flux tube has attractive flux tension, and that competes with the magnetic Coulomb repulsive force. So the size of this composite total monopole is determined by their balance. And actually, this composite magnetic monopole is very similar to what have been studied in this Saraswat paper, and I also studied earlier. So by this experience, we sort of came to this problem. So in the J from 0 to 1, in this two-dimensional space of gauge groups, U1 gauge groups, you can associate one unit vector to the each one U1, and there are U1 0 and U1 1. And the mass eigenstate is given by this diagonal. So equal weight you add. This is a mass eigenstate direction in the gauge group space. And orthogonal one is broken gauge group, corresponds to broken gauge group. So this vector corresponds to broken gauge group. This one corresponds to unbroken gauge, diagonal gauge group. And so the original lattice point vector, so U1 0 has the diagonal part 0 mode and this one, the broken one. And U1 1 has 0 mode and unbroken charge minus unbroken charge. So this is what I was telling. So if you have magnetic monopole in this basis, so you have unbroken flux and broken flux. So broken flux must go from 1 and absorbed into 1. And so schematically, just following the flux flows, magnetic flux flows, so unbroken one goes out, but broken one in this basis has to come from somewhere and go into this monopole. And this flux tube has tension and pull them, and that counters the magnetic repulsive Coulomb force. And by the balance, you can estimate the size. So by the way, this has a fractional magnetic charge, which is okay in the UV theory, but leads to the inconsistency. The Dirac string become apparent. So it's low energy theory. There's a unit charge Dirac quantization condition. Okay, so that's the main idea.
Pratik should the petty finish. Means Aditya is petty finished.
What?
So,
Yeah, must prepare that.
sorry. Any question or I couldn't hear very well. What did you say? Or nothing. Okay. So so yeah, we can. Oh, this is more actual picture. So you can estimate the width of the flux, magnetic flux, and actually it's compatible with magnetic monopole. So the composite magnetic monopole size. So flux actually divert inside the composite magnetic monopole. Yeah, so this is the kind of main result. And you can consider n equals 3 case. Schematically, you can see how fluxes are conserved, broken fluxes are conserved, and broken fluxes are going out. You can also consider n equal to 4. Now, our interest would be large n. But actually, in the large n, it becomes more and more difficult to follow the mass eigenstate and flux. Yeah, basically because discrete Fourier mode, the mass eigenstates, these are made of sine and cosine, so they can be irrational. So irrational charges with irrational and magnetic flux tubes with irrational charge binding number. I haven't figured out how to treat them. But actually, the magnetic flux in the original tube also can be a solution. So we are not really getting this whole system as a solution, but part by part Dirac monopole as a solution and flux tube as a solution. And then basically the order of magnitude estimate for the size by balance of the forces. So you can use the original basis and estimate the size of this composite monopole at large n. So continuum limit is achieved by taking the lattice points infinity, but making the lattice spacing 0, so that the total circumference of the circle is fixed. And composite monopole size is determined by the balance between magnetic Coulomb force and flux tension as like the same way. And yeah, as I said, it's a little bit difficult to keep track in mass eigenstate basis, but crude estimate is possible in the original J basis. And the size turned out to be like lattice spacing, which goes to 0 in continuum limit, which looks consistent. Okay, so yeah. So to summarize, the unit charge Dirac magnetic monopole in the deconstructed model is a composite of n constituent magnetic monopoles, each have 1/n magnetic charge in the UV theory. And magnetic Coulomb repulsion of unbroken U1 is competed by magnetic flux tube tension of broken U1s. The size of the composite magnetic monopole is determined by the balance between them. Large n limit or continuum limit is around the order of lattice spacing. So further directions. So as I mentioned, in larger n, there appear irrational charges and irrational winding number of magnetic flux. And I still haven't understood how to treat them. So it would be nice if one of you know how to treat them. And also, not only this composite magnetic monopole in this deconstructed theory, various extensions in various U1, multiple U1 gauge groups have been studied. And hopefully this, this looks quite interesting. The magnetic monopoles connected by magnetic fluxes. So it may have interesting cosmological scenarios like other monopoles or strings, cosmic strings played for some interesting scenarios are there. It may add some new scenario. And well, a little bit formal side, there's something called weak gravity conjecture from string theory swampland program. So this is basically saying gravity is the weakest force. And in this model, actually the four-dimensional gauge coupling is divided by square root of n. So you'll get very small four-dimensional gauge coupling as n goes to large, and it's at first sight a little bit worrisome for weak gravity conjecture, the gauge force becoming weaker and weaker. But actually, this factor also appears when states the weak gravity conjecture condition in U1 to the n theory. So actually, in this deconstructed theory, the weak gravity conjecture is respected if you start from UV theory, which respects the weak gravity conjecture. Okay, so